You know, most people have this picture in their heads. They imagine that someday, maybe a few hundred years from now, some brilliant engineer is going to crack the code on a really powerful energy source. Antimatter, advanced fusion, something spectacular and enormous and world-changing. And the moment that happens, we are going to start welding together these colossal metal arcs, loading up 1,000,000 brave human beings, and firing them off toward Proxima Centauri or Alpha Centauri or some beautiful little rocky world 4 light years away. The assumption is that energy is the only lock on the door. Find enough energy, and the door swings open wide. I want to sit with you today and really look at that picture carefully, because there is a brutal physical reality hiding inside it that almost nobody talks about, and once you see it, you cannot unsee it. The problem is not just having enough energy. The problem is what happens to the energy you do not successfully use. And in our universe, under the laws of physics as we understand them, that wasted energy does not simply vanish. It turns into heat. It always turns into heat. And if you are sitting on a small rocky planet when that happens, the consequences are not inconvenient. They are catastrophic beyond anything the human mind is wired to naturally grasp. Let me start by telling you something about the numbers involved in crossing interstellar space, because the numbers are where the story really begins. The nearest star system to our sun is about 4 light years away. A light year is the distance light travels in 1 full year, and light moves at 300 million meters every single second. So 4 light years is an almost incomprehensible distance. To cross it in any reasonable span of time, a time short enough that the people who board the ship might actually live to arrive, or at least their grandchildren might, you need to get that ship moving at a very significant fraction of the speed of light. Physicists and engineers who work on these ideas often talk about 10% the speed of light as a kind of rough minimum target, not 10% of some moderate speed, 10% of the speed of light itself. Now a generation ship, a vessel large enough to sustain a living, breathing, reproducing human civilization for the journey, is not going to be small. You are talking about something with a mass perhaps in the range of 10 million to 100 million metric tons. A floating city. A self-contained world of metal and water and soil and air. And to get that object moving at 10% the speed of light, you apply the laws of physics. Specifically, you apply kinetic energy calculations, 1/2 times mass times velocity squared, and when you do, the number that comes out is somewhere in the range of thousands of yottajoules. A yottajoule is 10 to the power of 24 joules. The entire human civilization today, all the power plants and all the engines and all the burning fuel on the entire surface of the Earth, produces roughly half a yottajoule of energy per year. So you need thousands of years' worth of all human energy production, concentrated and delivered to a single spacecraft. That is the scale we are genuinely discussing. Now here is where most conversations about interstellar travel simply stop and say, well, we need a really powerful engine, and that is true. But there is a law of physics that every single engineer on Earth knows intimately, and that every starship dreamer needs to confront directly. It is called the second law of thermodynamics, and it does not negotiate. The second law tells us something profound and uncomfortable about every physical process that involves energy conversion. No machine, no engine, no reactor, no process of any kind is 100% efficient at converting stored energy into useful work. There is always a fraction, and in most real systems it is a very significant fraction, of the input energy that gets released not as useful propulsion or useful electricity, but simply as waste heat. This is not an engineering failure. This is not something we can solve with better materials or smarter designs. This is written into the fundamental structure of physical reality. The entropy of a closed system always increases. Every conversion loses some fraction to thermal disorder. Every time you burn fuel or split atoms or annihilate matter with antimatter, a portion of that released energy becomes disordered thermal energy that spreads into your surroundings. Let me give you an image that I think captures the physical situation very clearly. Imagine you are living in a small sealed apartment on a brutally hot summer day. The walls are insulated. You cannot open the windows. The room is already warm and uncomfortable. Now imagine that someone tells you the solution to cooling the room is to bring in 10 massive industrial blast furnaces and fire them all up simultaneously inside the apartment, because you need that power to run a tiny plastic fan sitting in the corner. The furnaces roar to life and pour out enormous thermal energy. The tiny fan in the corner does spin. It works perfectly. The mechanism is a complete success from a pure engineering standpoint, but the blast furnaces are dumping 10,000 times more thermal energy into that sealed room than the fan is removing. The furniture catches fire in seconds. The walls begin to soften and buckle. The air becomes a superheated plasma. The fan is still spinning, technically, right up until the moment everything melts. The mechanism worked. The environment was destroyed by its own power source. That is not a metaphor chosen for dramatic effect. That is a physically precise description of what the thermodynamics dictates would happen if you tried to generate interstellar propulsion energies on the surface of the Earth. Think about what it means to produce those thousands of yottajoules of energy down here on the ground. Even if your antimatter factory or your fusion reactor is extraordinarily efficient by any standard we currently know, even if it converts 90% of its input into useful thrust energy, that remaining 10% lost as heat is still hundreds of yottajoules of pure thermal output dumped directly into our local environment. Hundreds of yottajoules of waste heat released into the atmosphere, and the oceans and the ground of a planet whose entire surface area is about 500 trillion square meters. You can do that calculation yourself. The numbers are not close. The numbers are not in the range where a little engineering ingenuity closes the gap. The numbers are so profoundly mismatched that the Earth as a living system is physically destroyed long before you have generated even a small fraction of the fuel needed for your ship. The oceans of Earth contain roughly 1.4 times 10 to the 21st liters of water. To raise all of that water from its current average temperature to boiling requires an energy input of roughly 3 times 10 to the 26 joules. That is 300 yottajoules to boil the oceans entirely. Your interstellar ship needs thousands of yottajoules of propulsion energy. Even at 90% efficiency, your waste heat alone exceeds the energy needed to boil every ocean on the planet several times over, and that heat does not politely wait to be distributed over geological timescales. It dumps into the system on the timescale of your energy production. The oceans do not gradually warm over centuries. They superheat rapidly, generating atmospheric steam pressure that the planet has no mechanism to release. The polar ice caps, which are already gone well before this point, are simply the first casualties. And do not think that the problem ends at boiling water. The rocky crust of the Earth has a melting point, depending on composition, somewhere between roughly 800 and 1200 degrees Celsius for common silicate rock. The kind of sustained thermal energy input we are describing does not stop at boiling water. The heat continues pouring into the system. The atmosphere becomes a dense, opaque blanket of superheated steam and vaporized minerals. The surface rock begins to flow. The upper crust transitions from solid to viscous liquid. The planet, from the perspective of any observer watching from space, begins to glow faintly in the infrared as its surface temperature climbs into ranges that geologists associate with planetary formation events, not with inhabited worlds. This is not a dramatic exaggeration added for rhetorical impact. This is the direct physical consequence of trying to concentrate and release cosmic scale energies within the gravitational well and thermal budget of a small rocky planet. The planet simply does not have the capacity to radiate that thermal energy away fast enough. The mechanism by which a planet loses heat is thermal radiation, and the rate at which it can radiate is governed by the Stefan Boltzmann law. A planet radiates energy proportional to its surface temperature raised to the 4th power times its surface area. Earth currently radiates at a rate sufficient to balance the incoming solar energy, but the waste heat from your Starship fuel production overwhelms that radiative capacity by many orders of magnitude. The planet heats faster than it can cool, and it heats without limit until the energy input stops, or the planet itself changes phase from solid to liquid to gaseous plasma. So we arrive at a very interesting and rather humbling physical conclusion. The laws of thermodynamics do not simply make interstellar travel difficult, they actively and aggressively prevent biological creatures from constructing the infrastructure needed for interstellar travel anywhere near the surface of their home world. This is not a pessimistic interpretation of the physics. It is what the numbers plainly say. Now a physicist does not stop at naming the problem. You keep thinking about the shape of the problem, about what it tells you. And this particular problem has a very interesting shape. The constraint is not about energy per se. You could have all the energy in the solar system available to you in principle. The constraint is about locality. It is about the fact that you are a small biological system trying to release and manage energies that are cosmically appropriate only for objects much larger than your world, in environments much more thermally permissive than your biosphere. There are ways around this that physicists and engineers think about seriously. You could build the ship and generate the fuel far away from Earth, out in deep space or in orbit around the sun where there is no planetary biosphere to destroy. You could generate the energy very slowly over millions of years and store it, keeping the instantaneous thermal output below the threshold that damages the environment, though the engineering of that storage presents its own staggering challenges. You could imagine a civilization that has spread itself off its home world before undertaking the interstellar project, so that Earth is not the factory floor. These are not absurd ideas. They are physically coherent directions. But the popular imagination, the science fiction vision, the casual assumption that a sufficiently advanced civilization just builds a big ship in a harbor somewhere and fuels it up and launches it, that picture is physically wrong in a way that the second law of thermodynamics makes absolutely non-negotiable. The waste heat problem is not a detail to be engineered away. It is a structural feature of how energy conversion works in our universe. Every joule of energy you release into a thermal environment ends up as heat in that environment. Every single joule. What this really tells you is something rather beautiful about the scale structure of the cosmos. Interstellar distances are not just far in the ordinary sense. They are thermodynamically far. The universe has, in a sense, enforced a kind of energetic quarantine on civilizations that are planet-bound. To play at interstellar scales, you have to become an interstellar scale entity first. You cannot remain a creature of one small warm world and simultaneously wield the energies appropriate to crossing the void between stars. The physics will not permit it, not because of any limitation in cleverness or ambition or technological sophistication, but because the waste heat generated by those energies is physically sufficient to sterilize and liquidate the very world you are standing on. That is the honest picture. And I think it is a far more interesting and intellectually rich picture than the simple story where energy alone is the problem. Energy is available in staggering abundance in the solar system alone. The problem is that we are delicate creatures living on a delicate planet, and the thermodynamics of efficiency means that wielding cosmic energies, always, without exception, produces cosmic thermal pollution. The universe does not give you something for nothing. It never has. And the second law of thermodynamics is perhaps the most uncompromising statement of that principle that physics has ever produced.